in the last lecture. So we talked a bit about the random variables. We talked a bit about some examples of probability, some basic concepts, probability space, and specifically the new thing which is called a sigma algebra of events. So, having said this, now we would move to our new concept today, which is called cumulative probability distribution functions, which are called CDFs. So, if the probability of every next event is getting, so say for example, for a certain random variable can take a certain values, and if the probability of every next value is being added, then it would be called as a CDF, cumulative probability distribution. And if the individual probability per event is being represented, then it is called a probability distribution function, PDF. So what is the difference between CDF and PDF? So let me give you a very quick example. um, if we try to plot I have cases of till 27th of April. I have cases of corona worldwide, corona infections, and say, let's say we start to try plotting Beijing. Since it is a CDA, since it's cumulative number of cases, we can always plot it like that. So if the peak has occurred, say for example in this case, you can see that the cumulative distribution function sums all the values of the all previous values, and it's always increasing. Either it is increasing or it is same. So when it will remain same when the previous values have no change. Otherwise, it can't decrease. So this is called this is the idea of a CDF. This is not a distribution function, by the way, because if it is a probability distribution function, then the sum should be between 0 and 1, and we can do it quite quickly. How can we do it? So just copy it. If I paste it over here, and I sum is 41468. So if I divide every number by 4, or, or sum of CS1, A1 colon CS1, I will get the probability distribution. Okay, that's the problem actually. I need to fix it. I'll put dollars. Yeah. No. Okay, let's forget that. The sum in this case is 41468. I mean, I'm an old school person. I make sure that things are working. So if I just drag it like that, 41468 till the very end, then it would be a probability distribution function. In this case, it is a CDF. So you can see that the scale is now between 0 and 0.016. So it would show the cumulative distribution, or the sum of all the probabilities. Um, we can always have a look at that. So this type of distribution function is called um, cumulative distribution function. And if we want to plot the events of individual day, then that type of distribution function is called probability distribution. So it's the difference between PDF and CDF. Say for example, for a coin tossing experiments, random variable can take 6 values, and for each value the probability is 1 upon 6. So for every case the probability is 1 upon 6. So if I plot it If I plot that, this shows a uniform distribution. So for each event, the probability distribution is just 1 upon 6, 1 upon 6, 1 upon 6, 1 upon 6, and 1 upon 6. So for 1, 2, 3, 4, 5, 6, the probability distribution is 1 upon 6. So this is called a PDF. And if I want to know the CDF, then it would be the sum of the previous one. So it would become like that. And let me try that. Yes. So so in this case, if I plot this, so this is called a CDF. So you can see that the sum of total probabilities will is equals to 1 in that case, and it will always increase or it will just stay there if the consecutive values are same, but it will never decrease. So these are the properties. One more thing I would really like to show you quickly is PDF versus CDF graph. So this is a very mm, where is the PDF? Okay, so this is the normal distribution. You know the PDF of a normal distribution, but the CDF of the normal distribution looks like that. So this is the PDF and this is the CDF. So cumulative distribution function will always sum to 100% and PDF will show the individual values. Similarly, for log normal distribution, this is PDF and this is CDF. For triangular distribution, we will be looking at that. This is the PDF and this is the CDF. By the way, I would love to you know take information from that page. I won't close that tab. So for a uniform distribution, just like we did for the coin tossing experiments, this is the PDF in blue and this is the CDF. Okay, excellent. Well, so we would be doing some. No, we won't be doing. We would be doing some Monte Carlo simulation. That's some kind of, and this is another I've used in my PhD. This is latent happy cube sampling. So we'd be doing that as well. Oh, not doing that. We would be doing in masters. So that's very interesting website, by the way. So these are the difference between PDFs and CDFs. So I draw that. I couldn't draw CDF right now because of the data. I have to subtract each consecutive value in order to get the value per day. What I can do for you is that I can look at it, look at a quick look at the data. Yes. So similarly, these are the total new cases for Pakistan for COVID till 28th of June. So if we look at them, I think bar chart would be a better one for the new cases. Come on, it's taking like forever. It has become non-respondent. Okay, just leave it for the time being. Let me show you from another resource. I should have a presentation over there. Mhm. Okay, so this could be thought. Okay, it's a percentage, but it can always be divided in by the total number to convert it into probability. So this can be thought as a PDF. So these are the reported cases admitted to AKU. So it's 26 February to 7 June. So data is per day. So you can see that the black points is original data, and the blue line is actually fitting the data to the points. So you can see that at the beginning, between 26th of Feb till 17th or 16th of March, there were a lot of cases in AKU, and there was a huge fluctuation. And number of patients admitted were all around 50, uh, between 25 and 85 per day. But now after that, after some time, due to some policies or AKUH being closed, the you can see that the data start decreasing. So something like that. I can give you a sensible one in PDF, I think. Mm, mm, you won't be able to understand that. Um, Once again, these are daily reported cases. You can see that. So the daily reported cases, we had data till 25th. So it was done on 21st of May. So we had data till 21st of May, and then we start to get some projections. Say in scenario number one, the projections were like that. In scenario number two, the projections were a bit different. So you can see that the data is per day. So I plot that. You can see the classical shape if it is doing that. So it is a typical PDF probability distribution function because it is changing words per day. And what I need to do convert, so it's a frequency product right now. But for converting it into PDF, what I have to do is to just sum this column and divide every element by the sum. So I will get the PDF for that. But the shape, the important thing is what we are talking about is the shape of the curve. Okay, now there are a couple of things. Coming back to our presentation, there are a couple of things I really want to make before continuing. First and the foremost thing is um, the difference in profile of PDF and CDF. You should be able to, you know, distinguish it quite clearly. First thing first, a cumulative distribution function is a sum of old probabilities, and it would always, at the end, it will always sum to 1 or 100%. A PDF is individual probability per unit day, or over here per value of the random variable x in this example, and it it shows the change in probability, relative change in probability with respect to individual values, whereas the change in probability as a sum or the cumulative change is being represented as a CDF. Now we'll go to the hardcore definition thing. That the distribution function is a function having domain R. Okay, a distribution function will always have domain in real numbers because random variables can take integer values. Random variables can take uh, so for a coin tossing experiment, the random value will always take integer values. But for a normal distribution, you need to find area under the curve. So it doesn't, and you cannot calculate probability at 1 or 2 or 3. You can always calculate probability between 1 and 2, between 1 and 3, between minus infinity and 2, between 2 and plus infinity, and so on and so forth. So domain should be in real numbers. The codomain is between 0 and 1, of course. because the output, so the input is always a real number. In that case, the output is probability, which should always be between 0 and 1. And the rule of correspondence, what is the rule of correspondence? It's assigning the domain to 0 to 1. So for every element of domain, the answer is between 0 and 1, such that f of x is equals to probability of x of x less than equal to x. So we need to find the probabilities of of the of that particular value of x till a fixed value. So we need to calculate probability of x till 4. So we need to find a, in case of discrete, so we need to find a probability of 0, 1, 2, 3, and 4. So less than equals to x. It has already been noticed that set x y is an event a is in an event in A, so it's a sigma algebra for all x belongs to R. Because if you sum any two events, the answer will always be in that sequence. The answer will always be the cumulative distribution function. Since an event A is assigned a probability by the definition of probability measure. So if we go back, quickly into the properties, so it has a number of properties. So distribution function of till minus infinity is 0 and at plus infinity is 1. So we assume that in real numbers all of the probabilities, all of the domain can be between minus infinity and infinity. So if it start any theoretical probability distribution, say it's assumed that normal distribution is theoretically between minus infinity and infinity. However, most of the values of normal distribution occur between minus 3.5 and plus 3.5, but theoretically, the distribution is between minus infinity and infinity. So at minus infinity, the cumulative sum is always 0, and at plus infinity, because we are summing it from left to right, at plus infinity, the cumulative sum is always 1. First thing. Second thing, of course, the cumulative sum cannot exceed 1, nor it can go beyond 0. Third property, it's a non-decreasing function of x. That is, f of x1 is always less than x2 if x1 is less than x2. You can see from that graph that these are non-decreasing function. The red color lines, लाल रंग की जो lines हैं, they are always increasing. They can never decrease. In contrast, the blue lines are decreasing. The change in shape in blue lines is quite evident. However, the red line will always increase or it will remain constant. Say, if there is no change over here, so it will always remain constant. So the interesting thing is when I was looking at profiles of different countries, I had to really look at the data and I had to think whether the peak has been passed or not. So in case of Mexico, in case of USA, in case of Iran, in case of China, in case of Canada, New Zealand. So when I looked at the data, I just plot the CDF. And if I'm over here, somewhere over here at the CDF, I believe that there won't be a larger change in per day cases. Why? Because if you draw a scale over here, you can see that the rate of change is quite low after that, beyond that point. So if you are somewhere over here, you can see that okay, the peak is almost 10. The total number of cases over here would be maximum of 10% more than the cumulative sum till here. So if I try to explain it from the data, and the great Microsoft Excel is still not responding, I don't know why. That's why I always prefer to use something else. Okay, coming back to the graph, and let's see whether it can bear the calculations, the load of calculation. Okay, just forget it, done it. So if you look at the total cases and try to draw a plot, oh god. Okay, I think things have been said and done, so I don't need that. Okay, so second property is f of x is always a cumulative probability distribution function is a non-decreasing function. Third property, it's a continuous from the right, that is f of x plus is f of x. So it is a property from calculus, then the function is right continuous or left continuous. So I'll leave it for the time being, um, because left continue. So the the left hand limit and right hand limit should exist to that point, and the function is always defined at that point, and limit of the left hand and right hand limit tends to the limit of the function. So these are the properties of continuity. Anyways, over here we can always say that when we are developing this line, so the red line, it's always continuous from the right. So whenever we have a point over here, it's always some point at the neighbor of that point. So you don't need to lift a pencil while constructing a CDF. The last property, f of x1 or x2. So if I okay, if you want to find a CDF between 2 points, say if I go back to that figure, and okay, I need to find CDF between this point and that point. So what I have to do is to subtract these two values, subtract the lower value or the smaller value from the bigger one, then you will get the CDF between these 2 points on x-axis, or in this case, random variables. In these between these two random variables, just subtract from the bigger number or the bigger outcome to the smaller one. This will give you the probability. Now, what is a PDF? A PDF as a rule of correspondence. Our rule of correspondence over here is it is the derivative or rate of change of um, the cumulative distribution function. When f of x is discontinuous, it always occurs as discrete random variables. It is necessary to call upon the impulse function. Okay, I will go back over there. We will look at it in a couple of minutes. So a PDF is always greater than 0. The total area under the curve is always 1 for a PDF. The distribution function is related to the density function via the integral. So this capital F is CDF, this is small f is PDF. In order to find PDF till a point x, you need to integrate it from minus infinity to x, and for any random variable over here is a sigma, and you will always get the integral or the sum till that point. Once again, the probability between 2 points is the integral between those 2 points. Over here, probability between random variable x1 and random variable x2 is the integral of the probability distribution function between x1 and x2. So these are theoretical properties uh, which I'm looking at. Um, let's wait for a minute and then see. Okay, so these are actually PDFs. So if I divide it by total number, so it's frequency over here. But if I sum all of these cases and divide it, then the scale would change into probability. But just to show you, this shows the per day change. So these lines shows the per day change. So it's kind of a PDF. Once again, this is again a PDF because if it's the shape, it's like PDF, because what in order to convert it into PDF, I have to sum all of the cases, say 1500 and then I don't know 1800 something, and sum it from the extreme left till the very end or at the right, and then sum it and then divide each value by that. So we will get the probability. So this type of shape. So it's over there. So I have calculated the PDFs actually over here. So per day change in case. I haven't talked about CDFs. This is again a PDF per day projected hospitalization and same. So you can see that uh, till there, till 21st of May, I think, or somewhere, 30th of May, the data is actually from the real data. This is the real data. That's why it has a lot of fluctuation in it. And then I try to predict after that. So these are the changes per day. How many hospitalization we would be needing per day in sin. So it shows that the hospitalization would peak around end of June or somewhere 20 June at a value of around 425 per day new hospitalizations in sin, and it would somehow go back to around 50 hospitalization per day by the end of by at the beginning of October. We can say that somewhere. These projections, don't take them. I mean, the projections are changing content continuously. So it's just an example to show you. This is a PDF. Why? First thing, very evident. It's is that it is decreasing. Now, these are the examples of PDF and CDF from the examples we show. These are the values of PDF and CDF from the examples we had in our previous lecture. So first thing is the three-sided die. So what is the chance of getting a one? So a random variable is one. Uh, so we cannot get anything less than one, because if you roll a die, you will always get something out of it. So you can't have zero. So it's and less than 2, so the second random variable, it has three random variables, 1, 2, and 3. So outcome B corresponds to 1, outcome C corresponds to 2, and outcome D corresponds to 3. Why I assigned why I assigned these values 1, 2, and 3? Because if you remember, the sum is actually 6 over here. And if I look at the probability expression for the distribution function, it is k from 1 to 3, p of xk, u of x minus xk. So this is the distribution function in this case, cumulative distribution function. So it is 1 upon 6 for 1, and then it becomes 1 upon 2 for 2, and it becomes 1 for 3 because I'm constantly summing it. Once again, so this is for distribution and this is for density function. So getting 1 is, I think, getting 1 has a probability of 1 upon 6, getting 2 has a probability of 1 upon 3, and getting 3 has a probability of 1 upon 2. So if you sum it 1 upon 2 plus 1 upon 3 plus 1 upon 6, you will get 1. These are the differences between expression for CDF and expression for PDF. So this is cumulative distribution function. It is always increasing. It is increasing in this case as well, but this is a density function. For a random variable in a wheel of chance, what is the random variable? The probability, it can take any value between the probability of coming, the probability of wheel rotating and getting any angle theta, which is theta by 360. We now define a random variable x by superimposing a standard clock. So theta by 30. For each angle change between 1 and 2, it's 30 degrees, because there are 12 sections of the so 12 times uh, 30 is 360. So we superimpose the wheel of change chance to a standard clock. So a random variable is theta by 30, because there are 12 values, and there are total 360 degrees. So what is the PDF expression? So you can see that it keep on increasing because we are summing it until so for one, I can draw it, I can solve it really quickly on Excel. Mm, So for example, it's a random variable that can take values of 30, give me a second, and then 90. So these are the angles, and I'm talking till 360. And the probability of each is x divided by 12. So it is saying that, give me a second, probability of theta is less than or equal to 30x is x upon 12. So these are the frequencies, and if I divide it by the sum, I need to fix it, I think. Then these are the individual probabilities, and if I sum them, I think I've done some mistake over here. I think it should be 630. Give me a second. So these are the values on wheel. These are not x. And the random variable can take intervals in steps of 30 only. X is 30-degree for each case. B2 upon 12. It should be C. B3 upon 12. So it would be so the similar sums. Yeah, that's why I'm saying that. So these are values on the wheel, which are 30 degrees and then 60 degrees and are 90 degrees. These are the random variables assigned to each value. So x can take value of so the change in theta for x would be in the intervals of 30. So we can get a simple probability for each event. So for getting 180, the probability is 0.08333. For getting 220, it's a since it's I can say it's an unbiased wheel, the probability for every one is same. And if I sum it, it will always give me one, because the total sum of the probabilities would always become one in that case. So the wheel of chance, in the wheel of chance example, the probability is always one. So that's why it's showing. And if I sum it like that, say this plus, okay, it's like that. And if I say it, it is this plus that value. So at the very end, this would become the PDF, a rough expression of the PDF if we draw a line. So this is the PDF for every angle. So for one, in this case, one corresponds to 30-degree. So the value, getting a value on wheel eh, of 30-degree, and I can always do what I can do is I can insert Control X, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are 12 sections. So getting a value of 30-degree, or the first section has the angle turning of 30 degrees, and if I divide it by 12, I will get 2.5. It has not it This is not a significant value, but the sum of all the turnings is 30. And if I calculate the probability or a PDF, it is something like that for every angle, for every occurrence. So for getting 1 or 30-degree, it is 0.0833. For getting 2 or 60-degree, it is 0.0833, and so on and so forth. And if I calculate the CDF of that, so CDF is an increasing line till it goes to 45-degree. So if you look at the presentation, it is the same. Okay, it say that draw it corresponding to 12. So I can do that. So like that, something like that over here and here. So they want something like that. And after that, they deliberately draw the line, or they extend the line, because after x equals to 12, the probability will always sum to 1. So because there is no change in probability, and at x equal to 12 we have got 100% or 1 on the probability axis. What is the probability for distribution? I mean, I've shown you, by the way. It's 0.0083, it's 1 upon 12. So if you divide 1 divided by 12, you will again get, mm, so it's 23. Why it's 23? You will get 0.0083. So the distribution function, or PDF, I've drawn. I just drew it in front of you. So it is something like that, between 0 and 12, and this. So you can always plot that. So we are talking about some common theoretical distributions. And thanks to Arsan Bari for that, by the way. Now we are talking about some common theoretical distributions, functions. The first and the foremost, I think I've explained it in a greater detail about PDFs and CDFs, and I've showed you a couple of examples. So the first and the foremost distribution, we know it very well. It's called a uniform distribution. How many parameters do we need to properly define a uniform distribution? We only need two parameters to define a uniform distribution, which is a maxima and a minima. So we need to have maximum value, and we need to have a minimum value, and define probability, which is 1 divided by b minus a. So the maximum minus minimum value will give the probability of each and every random variable lying between the minima and the maxima, and the probability is zero otherwise. So this is actually called the uniform distribution, or this is called triangular distribution. What is a triangular distribution? It's a specific type of distribution, uh, in which, and it's always used in situation when the exact equation of the distribution, exact form of the distribution is not known, but an approximate value of is known for the minimum, maximum, and most likely value. The triangular distribution, it is denoted by a, m, and b. So triangular distribution needs three parameters. a is the a is the minimum value, m is the median value or the most likely value, and b is the maximum value. So it's slightly different from the uniform distribution, and it is a, m, and b. So if m, or the most likely value, is shown as a hump, or as a vertex of a triangle, a is the minimum value and b is the maximum value. If you need to find the probability of a number, any number between a and m, you need to use this formula. If you need to find probability of any number between m and b, you need to find this formula, use, otherwise it is zero. So let's assume it's a class task. So everyone please wake up. Let's assume there's some problem in that. Yeah, I need to put it back. We are looking at triangular distribution. Let's assume a triangular distribution is drawn between 50 and 60. So I'm talking about A is 50, B is 60, and M, the most likely value, is 53. So can you guess the shape? Can you guess the shape of a triangular distribution when minimum is 50, maximum is 60, and the most likely is 53? It should be something like that over here, because the most likely value is close to the minimum value between 50 and 60. What would happen if it is 58? Hmm.
Same.
सर मिरर इमेज हो
No,
जाएगी जो भी था.
58 की सूरत में ये जो hump है m का, ये इस तरफ हो जाएगा. The
यस सर
diagram
इसकी
would be something like that.
यस सर
So
जो है उसकी मिरर बन जाए.
it's a flipped image of a to m. So if m comes over here, the most likely value, if it is the most likely value, then there should be a hump over here rather than there. So this is to just to show you this. So for a triangle, we need 3 points on which 2 points lie on the same line, and third point not lying at the same line. So this is a general principle of drawing a triangle. So a third point can be a variable point between a and b. Any point between a and b can become the most likely depending upon the distribution. Now, if we have an Excel sheet, if we have minimum values of 50 and highest value of 60, can you calculate the probability of x equals to 52? So a random variable can take any value between 50 and 60, and the most likely value of that random variable is 58. What is the probability of getting x equals to 52? So what we have to do is very simple. Just put 50. We are talking about 52 or 53. I forget.
52.
So we put 52 in place of x. We put 50 in place of a, and we put 60 in place of b, and find the probability 0.05. And what if I change the median? So I fixed everything, and I want to find the probability of x equals to 59. So the value should be higher. We anticipate the value we obtain between these 2 points would be a higher value because it is closer to the median, and I expect the values
यस सर यही बोल रहा था मैं.
and I expect the red colored values to be lower because
सर
they are
9 अपॉन
far.
40 है.
Hmm?
9 अपॉन 40 है.
9 upon 40 for 59.
हाँ, अगर डिफरेंस 9 है तो वैसे वो 18 अपॉन 80 होगा, वो 9 अपॉन 40 होगा.
Okay, so it is 0.225 in this case, and you can see that it is 0.05 and it is 0.225. So there is a big difference between these two values. Similarly, it would be somewhere around zero point 0.2 or zero point 0.3 at 57. So this is how we can construct a triangular distribution, and this is how we can solve or calculate the PDF of a triangular distribution. How can we find a way to get the CDF? Let's assume it to be a discrete function. So I will take x like that, and I will take f of x rather than p of x. I'm writing f of x. So f denotes the CDF, and just calculate probabilities of everyone. Okay, I can do that like now. So it would be easier for you to understand. Calculate individual probabilities and then calculate the cumulative sum function. So we have the value for 52. Class में से मुख्तलिफ students, just different student take different values and then solve it for me and call it out. I have to fill this table.
सर ये 59 की वैल्यू मेरे पास 0.10 आ रही है.
0.10 आ रही है. Is there anyone else? Just try putting. What you have to do is to just to put it in this formula. So you know A, it is 50. You know B, it is 60. You know M, it is 58. You just need to put an X, and that's all. And then just think about whether the value of X is greater than M or less than M. If it is less than M or between A and M, use the formula at the top. If it
सर
is
पॉइंट वन ही
between
आ
M
रही
and
है.
hmm?
पॉइंट वन ही आ रही है सर.
Okay, so it is 0.1. And what about probability at 60? It should be 0. It should be 0 as well. इसका सम 1 आ गया. अब इसकी शेप देखते हैं हम लोग. इसकी शेप कैसी होनी चाहिए? देखिए ट्रायंगुलर डिस्ट्रीब्यूशन बन रही है.
यस सर.
हम सब ने मिलकर इस सवाल को सॉल्व किया है.
यस सर.
सबने अपनी सलाहियतों के मुताबिक सवाल की तैसी करी है. लेकिन देखें इसकी जो शेप है वो ट्रायंगल जैसी आ रही है, और मैक्सिमम
Yes, sir.
प्रोबेबिलिटी इसने 58 पे टच करी है. और देखिए 58 पे मैक्सिमम प्रोबेबिलिटी उससे ज्यादा कहीं नहीं होनी चाहिए. 0.2 कहीं और है. और अगर हम देखें तो 59 पे, चूंकि उसको 60 पे जाना था, तो 59 पे इमीडिएट ड्रॉप हुआ. देयर इज एन इमीडिएट ड्रॉप आफ्टर 58, एंड बिफोर दैट it was an steady increase, but since we need to finish at 60, there was an immediate drop. That's why the probability at 59 is very low. It's 0.1. whereas the probability is at 57 is quite high as compared to there is only one integer difference from 58. So 57 is one integer behind and 59 is one integer after. However, there is a striking change in the probability. Even if you go to 57.5 and if you look at 59.5, this change will even be even more evident. So probability of 59.5 will be even lesser than zero point 0.1 and probability at 57.5 will be even greater than 0.175. So these are some observations which we have learned. So if I sum the previous values, then I will get the what's happening. Not C4, it shouldn't be like that. Okay, E3 plus C4. Okay, there is some issue why probability is getting more than one. I don't know. There might be some. Okay. Anyway, so this is actually the sum of it, and then if we stop till here, so you can see that after 10 or 11, the probability is getting exhausted. There is some problem in the formula, and I really need to look at it. But if you see that, you can see that the probability it should stop at 1, and it should continue uh, to be at the same point rather than stopping at 1.10. It should stop at 1.00, and then it should continue the pattern. So this is the CDF, and this is the cumulative distribution function, and it cannot be. You can see that as from the values, you cannot have the next values lesser than or equal to the previous value. It can be equal to, but it cannot be less than the previous value. So this is how you can solve a simple problem, and this is how we can construct an exponential distribution. So I don't know about you, but I think today's lecture will help you to connect between PDS, CDFs, and to do it by hand. So the best thing is for today, what I think is now you don't need to afraid from PDFs and CDFs. You can always do them by hand. Just take any value of m, just take any value of x, and then try finding the probabilities. The last but not least is the normal distribution because oh God, it took so much time for me to explain a couple of slides. So it's a normal distribution, and the PDF of a normal distribution is like that. And the domain of normal distribution is between infinity and minus infinity. So what you have to do is that you can do it quite easily. Everyone need to to actually sort this bug out. ये वन से बड़ा क्यों आ रहा है? Just try sorting this bug. Okay, this is triangular, and what is this? This is wheel of chance. Now we are talking about what normal. So when we are talking about the normal distribution, this is the PDF of a normal distribution. And always remember the domain is for normal distribution. It can't be discrete. 0.001, 0.002. So these can be thought as the values of x. No, there is one more thing I would like to, which has not happened before. It is minus minus 0.01, minus 0.1, minus zero point 0. No, I think it's not really. Anyways, if I start from zero, I just wanted to, because there's not much time left for me. If it is zero and then 0.01 and then I will sort it out. So if there are a couple of values, and if you go, because this will only show one side of the normal distribution. The best thing about the normal distribution is the random variable can take negative values as well. Anyways, for the time being, just talking about the positive values. So if you so the CDF or the PDF, sorry, the PDF for the distribution is 1 upon 2 pi sigma e to the power minus x upon m square divided by 2 sigma square. So what is m over here? So for if you go back to the first distribution, how many parameters do we require for a uniform distribution? Minimum, maximum. How many parameters we require for a triangular distribution? Minimum, maximum, most likely. How many parameter we want to describe an exponential distribution? Lambda or m in this case, which is mean and also the standard deviation. How many parameters we need to describe a normal distribution? We need two, mean and standard deviation. If we have the mean and if we have the standard deviation, we can completely define a normal distribution. So m is mean and sigma is a standard deviation. So we can take any value, say mean is, it should be a dummy data, and a standard deviation s or sigma is say mean is 0.5, 0.01, something like that. Now we can construct a probability distribution function by using the simple formula. So what is the simple formula? 1 upon 2 pi sigma in the square root 1 divided by, do they have SQRT or something? Okay, that's good. Square root of 2 multiplied by pi. I don't know whether pi is defined as over here. 3.14159 multiplied by sigma. It should be fixed. Okay, and it is being multiplied by a factor e to the power minus x upon m square divided by 2 sigma square. So it should be multiplied by exponential, and this is outside minus outside. Yeah. Yes. Negative exponential is x minus m square divided by, so x, what is x? X is over here, minus m, what is m? M is over here, square at 2 divided by, is it inside the exponential? 2 sigma square. I don't know. I mean, I forgot the formula. Just write down the CDF, PDF of. It's a bit risky over. I think it should be over here. So, so 2 sigma square is not in the exponential. Thank you very much. Divided by 2 into sigma square I need to do is to put another bracket. Oh God. Okay, I have to break this formula again now. Insert is equals to, okay, it has an issue. That's the problem. So it says that exponential minus a2 is over there, divided by c2. Okay, it's saying c, it should be d then. d2 because it is n, and it should be e. Again, there is an issue. I think it's because of the brackets. Again, there's an issue. Okay, I will, now the time is actually passing. I will sort it down and then I will, so this is just a simple typo. I will sort it down and then I will send it to you, the sheet for the wheel of chance, for the triangular distribution, for the exponential distribution, and the normal distribution. It's just a typo. A very quick thing at the end, which I really want to push, is come on. Do you have Minitab? I mean, I think you are familiar to Minitab, if I'm not wrong. Minitab है तुम लोगों के पास? हाँ भाई,
Yes, sir.
Minitab है, यूज तो किया है ना तुम लोगों ने?
Yes, sir.
Have you used Minitab? Okay, thank you.
Yes, sir.
So we can always get the random data just to show you a very quick picture. So rather than doing it ourselves, we can always generate random data from any distribution we want. So we were actually doing, so there should be triangular over there. I think triangular distribution is very simple. That's why they might not have it.
Sir, second last है शायद.
Second last, thank you. Triangular distribution. They have chi-square, they have normal, they have F distribution,
Sir,
T distribution, uniform,
sir, second
binomial.
last.
हाँ देख लिया मैंने, देख लिया. And they have Poisson distribution, they have exponential distribution, gamma distribution. So for example, we want to look at normal. So you know that how many number of rows to generate, say 10,000, I don't know, a lot of zeros. In which column I want to store? I want to store it in C2 or C1. What is the mean? Mean is 5. What is the standard deviation? Standard deviation is 1.2. It would generate a lot of values that are sampled. So if you just eyeball the value, just look at the value. So if in values को देखिए, मैं Excel में इनको paste कर दूं, just try having a look at the values. तो आपको 12 मिनट है, मैं चले जाते हैं, Excel को तो बुखार हो जाता है बेचारे को. तो आप देखिएगा, मैंने मीन कहा था तकरीबन 5 के करीब, 5 कहा था शायद. सो मीन 5 है, तो आप देखिए ज्यादातर वैल्यूज जो है वो, if you know mean plus minus 1 standard deviation में तकरीबन we will get almost 66.6% of the values between mean plus minus 1 standard deviation. So that would be 6.2 and that would be I think 3.8. Between 6.2 and 3.8 you will get most of the values. And if you remember, if between 5 plus minus 2.4, which is 2 times the standard deviation, you will get almost 95% of the values. So you can always check that. Most of the values would be between 3.8 and between 6.2. So if you just eyeball it really quickly, and if I have to make a line or a simple line of it, just dots, and you can see that most of the values are occurring into the similar scale. So if I want to see that graphically, and if I really want to draw a histogram, then that histogram should always have a mean at, you know, that this is a normal distribution and mean is around 5, and you know that between 3.8 and between 6.2 you can find almost 68% of the values, and so on and so forth. And if you, so you can find between 2.4, what is 5 minus 2.4 is 2.6. Between 2.6 and 5 plus 2.4, it's 7.4. Between 7.4, it should be coming somewhere, it's 7.35, and 2.6, it's over here. 2.6 is right there. So you can find almost 95% of the value. So it is evident from it. So this is called sampling from a distribution, and looking at the sample. So you did the sampling by yourself, so it's quite evident. But we can do that. So for a triangular distribution, number of data points to generate, say 100. What is the lower end point? It is 50, if you remember. What is the mode? It is 58. What is the upper end point? It is 60. Store in columns. Okay, store in C2. So we have values from a triangular distribution. And once again, if you want to look at the histogram of it, the histogram should look like a triangle. So in this case, it's not quite clear, but you can see because of the random sampling. Let me sample a bit more. So more the sample, the better the visualization. Because it was only 100. Let me do it for 10,000. And if I really want to put a histogram, for C2, then you can see that the shape of triangle is more evident from here. नजर आ रही है? So the peak would occur at around 57.9 and 58.1. So this is nearly the peak where the peak should be occurring. Is it visible to all of you? हाँ भाई.
Yes, sir.
Yes,
So
sir.
this is called sampling from a distribution, and we can always make use of the samples to look at different aspect of the distribution. So you will be looking at it quite a lot in your upcoming lectures. That's why I'm putting stress on how to do sampling, how to do stuff like that. And that's all for today. An exponential distribution requires only a single parameter. And what is that single parameter? It is lambda, if you remember. And lambda is the mean of the distribution, and lambda is also the standard deviation of the distribution. So in this case, it is denoted by m in that example. So m is the mean of the distribution, m is the standard deviation of the distribution, and the probability density function for that distribution is like that. So for example, if we have an exponential probability distribution, so I say that I'm talking about inter-arrival times and the probability of inter-arrival times, then 1, 2, 3, 4. So we are starting at 9 a.m. So let it be like that. And okay, I need to change it in time. So we start at say let's talk like that. Let's write that 9 a.m. at 9:10, and then at 9:20, and at 9:30. Okay, this is another problem. Delete. Now there is some there, so between 9 and 10 a.m. in the morning, the probability on average we will get 5 customers. Say for example, m is 5. So what is the probability of getting 2 customers? What is the probability of getting 0 customer? What is the probability of getting 4 customers? So this is not x, by the way. Once again, it might confuse you. This is just the time, and this is x. So what is the probability of getting 0 customer between 9 and 10? What is the probability of getting 1 customer between 9 and 10? What is the probability of getting 2 customers between 9 and 10? And so on and so forth. So 0 customer between 9 and 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the probability of getting 10 customers between 9 and 10? So this is actually the random variables. And if you remember, in contrast to binomial distribution, which is bounded below and bounded above, exponential distribution is only bounded below. It cannot be negative. It is bounded by 0, and it is unbounded above. So in principle, there can be infinite customers between 9 and 10, but there cannot be less than 0 customers between 9 and 10. Do you get this point?
सर एक बार वापस रिपीट कर देंगे?
Okay, so you in theory, just like a normal distribution in theory is between minus infinity and infinity. However, most of the values occur, almost 99.9995% values occur between minus 3 and 3. Similarly, it is bounded, it is unbounded from the negative infinity, and it is unbounded from the left as negative infinity. The normal distribution is unbounded from the right as positive infinity. For a binomial distribution is bounded below, and a binomial distribution is bounded above. For a coin tossing experiment, it is bounded below by heads or tails, and it is bounded above by heads or tails, whatever. So you can have either head or tail. So the random variable could be either getting a head or getting a tail. In die rolling experiment, it is bounded below by 1. You cannot have a 0 in a die rolling experiment. You can have either 1 or 2 or 3 or 4 or 5 or 6. So it is bounded below by 1, and it is bounded above by uh, sorry, it is bounded below by 6, and it is bounded above by 1. So these are the problems with the random variables. When we are talking about binomial distribution, a binomial distribution is always bounded above and bounded below. But in an exponential distribution, it is bounded below because you can't have negative values, but it is not bounded above. So in principle, what does it mean? How can we translate it? So if I'm talking about getting customers in the inter-arrival time, so it is mostly dealing with inter-arrival time as it is written over here for an entities, and that's why it is very important for discrete event simulations. So we will be getting to we will be dealing with discrete event simulation in our next lecture. So that's why I'm a bit concerned about that. So bound exponential distribution is bounded below by 0, but it is in principle, in theory, unbounded from the higher value. So you can have two customers, you can have five customers, you can have 100 customers, you can have a million customers, you can have, in theory, you can have an infinite number of customers at a certain time interval. Another property of exponential distribution and Poisson distribution is the concept of time. So when we are talking about uniform distribution, about coin tossing, and about die rolling or anything else, we don't talk about time. For a triangular distribution, we didn't consider time, but for an exponential distribution, you can see that I make a time variable between 9 and 10. What is the probability of getting zero customer? Between 9 and 10, what is the probability of getting one customer, two customer, three customer, and what between 9 and 10? And you can extend it in principle, to be very honest. So let it be like that, between 251 customers. So the probability, so the most likely value of customers between 9 and 10 is 5. So let's try finding these values by using an exponential distribution. So what is the PDF? It is 1 upon n e to the power minus x upon m. So it should be 1 upon m. What is m? It is g2 multiplied by exponential of minus x upon m. What is x? Minus x upon m. Okay, the problem is m is d2. It is a problem, but the problem is I need to fix d2. Otherwise, there would be a problem. And I need to keep variable value b2. So if I, so you are getting probabilities, although they are very low, but at around, so if you plot it, or if you plot it against x, look, this is a typical shape of an exponential distribution. Let me scale it down for you because there were a lot of value or just like that, and that's all. So this is, you can see as it's a typical shape of an exponential distribution. Let me take a bit lesser values, say till, okay, till 30, and then plot it again. Okay, so this is an example of an exponential distribution. An exponential distribution look like that. So this is the PDF. That's why it is written P of x. What would be the CDF?